day, everyone. Welcome to class once again. Today we shall continue probability, which we have started earlier. And the last time we were able to talk about the mutually exclusive events, where we added probabilities together, the independent events. I was able to also establish that probability measures the degree of occurrence of an event. Also, that if we sum probabilities together, we have 1, and probability does not exist 0 and 1, exceed 0 and 1. That is, 1 is the highest probability you can have, 0 is the lowest and the last. And when probability of an event happening is 1, it shows that it is a sure event, that it will definitely happen. And if it is 0, there is no tendency that it will happen. That is, it's not going to happen at all. So today we move on to probability of success and failure. And that goes to the third property where I was talking about the other time, that P plus Q equals to 1. P represents the probability of success and Q represents the probability of failure. So what does the success mean? If I'm interested in an event happening, that is the success. If it does not happen, that is the failure. Such that if we now want to get our P, it gives us 1 minus Q. P is going to be 1 minus Q, and also Q is 1 minus P. So we need to look at questions where this is really applicable. That is, when we see question, how do we even use this information? So an example we have below says, the probabilities that 3 boys pass an examination are 2 over 3, 5 over 8, and 3 over 4 respectively. Find the probability that 1. All the 3 boys pass. 2. None of the boys pass. And 3. Only 2 of them pass. Now, for us to solve this, well, if they mention the names of the boys, it's easy for us to say, okay, Ade did this, Shola did this, Matthew did that. So here, let the 3 boys be A, B, C, respectively. So that means the probability that boy A pass is 2 over 3. Probability that boy B pass is 5 over 8. Probability that the third boy pass is 3 over 4. So from the question, they've already given us the probabilities. So what do we do? Probability that A will pass is 2 over 3. So what's probability that A will not pass? We need to find that. It's important that we get that value, that A will not pass. So if A will not pass, then that's going to give us 1 minus probability that A will pass. So 1 minus 2 over 3 will give us 1 over 3. Just do 2 minus 3, that's 1. It gives us 1 over 3. It's easy for us to subtract like that. So probability that B will pass is 5 over 8. So what's probability that B will not pass? 5 minus 8, that's 3. So that's 3 over 8. Just like saying 1 minus 5 over 8. That is going to give us 8. Then 1 in 8 is 8. 8 times 1, 8. Minus 8 in 8 is 1. 1 times 5, 5. So that gives us 3 over 8. Don't forget, this is what I'm using now. Just P is 1 minus Q. Q is also 1 minus P. So for me to get probability that E, or then say, it did not pass, it's going to be 3 over 8 when I subtract it from 1. Probability that C did not pass, probability that C passed is 3 over 4. Probability that C did not pass will now be 1 minus 3 over 4, which will give us 1 over 4. So the moment we have gotten the information for the success and the failure, we can move on easily to solving the problems. But don't forget, whatever they give us, even if it is the probability of failure that was given, then find the probability of success. If they give us that of success, make sure you get probability of failure, because the question that they will ask you might be different or might vary in different cases. So the first question is, all 3 boys pass. So I'm representing it like this. Probability that A pass, B pass, and C pass. 3 of them passed. So what do we do? What's probability that A passed? 2 over 3. Times, what's probability that B passed? 5 over 8. times what is the probability that C passed? 3 over 4. So the rest is just to simplify. 3 here can cancel this 3. 2 here 1, 2 in 8, 4. So that's 5 at the top. 4 times 4, 16. Again, 3 here can cancel this 3. 2 here 1, 2 in 8, 4. So 5 times 1 is 5, 4 times 4 is 16. And that is the final answer for that. The second question, none of the boys passed. If none of the boys passed, it means A failed, B failed, and C also failed. That is what I'm now using this complement for. That is, probability that A fails, that is A did not pass, B did not pass, C did not pass. That would be the opposite of A pass, B pass, and C pass. So what do we do in this case? We just come here. What's the probability that A did not pass? 1 over 3. Probability that B did not pass? 3 over 8. Probability that C did not pass? 1 over 4. So if we move here, we just place it there. 1 over 3 times 3 over 8 times 1 over 4. That is why it is necessary for us to first get those values. Then we can now just be placing it inside the equation. So 3 here 1, 3 here 1. 1 times 1 here is 1. 8 times 4 is 32. The third question. Only 2 of them pass. What does this mean? Just like when we were picking the balls in the last lesson. If only 2 of them pass, we don't know which one. Is it A and B? Is it A and C? Is it also B and C? Which of them? So it's either A pass, B pass, and C did not pass. Don't forget there are 3. We have to consider 3 of them. Or A pass, B did not pass, and C passed. Or A did not pass, B passed, and C also passed. So there are 3 possibilities for that. These 3, we multiply them here, or that is, it could also be this, or be this. If only 2 of them pass, only 2 pass, that means the event is going to just be mutually exclusive. It's either these 2, or these 2, or these 2. So, probability that A pass is 2 over 3, multiplied by B pass, 5 over 8. But C did not pass, so we have to pay attention here and not make mistake to be picking 3 over 4. What's probability that C did not pass? That is 1 over 4. Come here, put it inside. Then we can now divide and simplify. So 2 here is 1. 2 in 8 is 4. So 5 times 1 up here is 5. 4 times 4, 16. 16 times 3, 48. The same thing goes here. This 3 can cancel this 3. 2 here 1. 2 here 2 here 1, 2 here 4. So that's 4 times 4, 16. 3 times 1, that's 3. And lastly, 3 here can cancel this 3. Then we have 5 divided by 32, 8 times 4. Looking for the LCM, 96 is the LCM. So 48 in 96, that's 2. 2 times 5, 10. 16 in 96, that will give us 6. 3 times 6, 18. Then 32 in 96, that is also 3. 3 times 5, 15. So have this together, we have 43 divided by 96. Now we move on to other scenarios under probability. We could also have an event of tossing coins. So I'll start with when we are tossing a coin. We could also toss 2 or 3 coins. So the event of tossing the coin, we need to get the sample space. That is, what are the possible outcome? A coin is either a head or a tail. A coin has 2 sides. If I toss a coin, it's either it comes on this side or this side. So it's either we have a head or a tail. So the sample space, because it is this sample space that helps us to know the total outcome and also the one that are favorable, depending on the question that's going to be asked. So if we are asked now that what is the probability of getting what's the probability of getting a head or a tail? So a head, what we just do is probability of getting a head is equal to how many heads do we have in the sample space? 1 over 2. Probability of getting a tail will also be how many tails do we have? 1. Then how many outcomes do we have altogether? 2. The first one we considered was the event of tossing a coin, and we noticed that we had just 2 outcomes. The sample space could either be a head or a tail. But in this case of tossing 2 coins, that is, you have 2 coins in your hand and you toss it at a time. Now I need to establish this, that the event of tossing 2 coins at a time is also the same as tossing 1 coin twice. That is, I could just, if I have just 1 coin and I need to consider this, I toss the first coin, get a record of it, okay, head, write it. Then the second time, okay, I still have a head, write it there. Just like that. So what are now the possible outcomes of that? This is the simple way of getting the sample space, because the sample space is very important. So I use S to represent the sample space, telling us the number of outcomes that we need. So by the time we get that, we'll be able to do, okay, this is the number of favorable outcome divided by total possible outcome. But we need to generate that ourselves. So if you toss 2 coins, 1 coin has 2 possible outcomes. So if I'm tossing it twice, it's going to give me, so this is how to get the sample space, 2 raised to power n. So if I'm tossing a coin twice, then so n is not representing the number of times. N, number of times. Don't forget, if you toss a coin twice, is equivalent to tossing 2 coins once. So my sample space is 2 raised to power 2 because I'm tossing this one twice, and that is 4. So at least this one helps me to know that I'm going to have 4 different outcomes. How do I now get that? This tree helps us to actually locate that. Create a head and a tail, because these are the 2 possible outcomes of throwing a coin. Head and tail. So on this one, extend it again. Head and tail. On this tail also, extend it, head and tail. I'm stopping here because I tossed the coin twice. Oh, sorry, 2 coins once or 1 coin twice. It's still the same. So just count like this. Head, head. That will be the first outcome. That is, if I toss the 2 coins, it's either I have a head and a head. So this is it. If I toss it again, it's either I have a head in the first place and a tail on the second one. So this is the head, tail, and this is how I got that. Head, tail. That's the next one. So if I toss it again, the possible outcome, it could also be tail on this first one and head on the second one. So it's going to give me tail, head, and also it will also be tail, tail. That is, the coins could turn tail on the first one and tail on the second one. So these are the possible outcome: head, 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 tail, tail, head, and tail, tail. So the question are now going to be asked based on our sample space. So for example, what is the probability of getting 2 heads? If I toss a coin twice or 2 coins once, what's the probability that it will give me 2 heads? Now we know that The sample space is this. Now from your sample space, how many have 2 heads? Just one. That is going to give us probability of having 2 heads is 1 divided by total possible outcome 4 divided by 4. The next question is, what's probability of getting 1 tail? Go to the sample space. How many have 1 tail? Tail, tail. So we have tail, 1 tail here, we have 1 tail here. So how many is that? 2 favors 1 tail, then total possible outcome is 4. So if I simplify that further, I have 1 over 2. 2 here 1, 2 in 4, 2. The C question says, what's probability of getting at most 1 head? So what does that mean? At most means the highest we can have is 1 head. So how many have 1 head? There's 1 head here, there's 1 head here. At most, the highest, what's probability that if I toss a coin, 2 coins, I'll have at most 1 head. I'm having 1 head here, I'm having 1 head here. So that gives me 2 of them, which is 2 divided by 4. Divide that 1, 2 here 1, 2 in 4, that's 2, 1 over 2. And the last one, at least 1 tail. What does at least 1 tail mean? What's probability that I will get at least the minimum of 1 tail? That is 1 tail and above. When they say at most, it means that particular thing and below. So if here I mean for this question C, if I had said at most 2 heads, that means I'm talking about 2 heads and below. So we have 2 heads here, that's 1. We have a head here and another head here. So that's making 3. But here, at least 1 tail means we have 1 tail and above. We have 1 tail here, we have 1 tail here, and we have 2 tails here. So it still covers that. At least 1 tail. So 1 tail, 2, this is another tail, 1 tail, and this is another tail, 2 of them. So 1, 2, 3 satisfies this. And that's why we have 3, which is favoring the question, over total possible outcome, which is 4. So the question can go on and on, but it still lies in what we have in the sample space, depending on whatever they ask us to look for. So the next one is the event of tossing 3 coins. Just like I said here, if you toss 3 coins once, we have the same result. If we toss 1 coin 3 times, we still have the same result. When we get to the event of throwing dice, you understand, because there is this Ludo game. When we have just 1 die, we play it twice. When we have 2, we just play once. So you count them and get the result. So here, if I'm tossing 3 coins at a time, or 1 coin 3 times, this is the way to get the possible sample space. So this is the sample space. Draw the head again and the tail. That's what I drew here. Don't forget, I said I stopped here because there were 2 coins. So I will extend it by 1 because I'm doing 3. So if it is 4 coins, just extend this one too. So here, head, then extend it. Head, tail. For the tail here, head, tail. Start from this head again. Extend it, head, tail. The tail here also, head, tail. Here, head here, head, tail. Tail here also, head, tail. There are people who can get it offhand without even drawing the tree, but this tree helps us to get it perfectly. So you just start counting. Now we have head, head, head. So that's the first one. Then head, head, tail, because you have not exhausted the possibilities here. Head, head, head. We still also have a tail, so that will be head, head, tail. That is the next possible outcome. Then, since we have exhausted this particular tree or this branch, we move to this one. Head, tail, head. That's how I got this. Head, tail, tail. Head, tail, tail here. That is head, tail, tail. Now I've exhausted the branches on this side. I move to tail. So this is tail, head, head, which is this. Tail, head, tail, which is this. So this branch is gone. Then I move to this part. Tail, tail, head, and that is what I have here. Tail, tail, tail. This is what I have here too. So the possible outcome for this is 8. Don't forget what I said. Sample space is always 2 raised to power n for coins, because the possible outcome for a coin is 2, either head or tail. Now, because I'm tossing it 3 times, my n is now what? 3. So my sample space will have 2 raised to power 3, and that is 8. And that's how I have 1, 2, 3, 4, 5, 6, 7, 8. So this will help you to at least know where to stop. So that you know that if you already have 8 different outcomes, then you are correct. So it's better to at least know where you are going. So if you have 4 coins, definitely we have 2 raised to power 4. That will be 16, and so on. The question is, what is the probability of obtaining 1, 3 heads, 2, 2 or more heads, 3, 3 heads, 1 tail? Like I said, there are different questions that could be asked here, but it will not exhaust the sample space. So let us consider these 3 examples. What's the probability of obtaining 3 heads? Go to the sample space. How many have 3 heads? Just 1. Just like if the question is, what's the probability of obtaining 3 tails? We have just 1 tail. I mean, one of the outcomes having 3 tails. So this 1 divided by 8, total possible outcome. 1, 2, 3, 4, 5, 6, 7, 8. Number 2, 2 or more heads. That is also talking about at least 2 heads. 2 or more heads is also talking about at least 2 heads. So this question could be rephrased. What's the probability of obtaining at least 2 heads? That's why I'm just writing like this to at least explain what I did here. What's the probability of obtaining 2 or more heads? So just go there. Where do we have 2 heads? 2 heads, 2 heads, 2 heads. Then also the one that have 3 heads is also there, because it is 2 or more heads. So that means we have 3 heads here, is part of it. We have 2 heads here, that's 2. 2 heads here, 3. And 2 heads here, 4. So that gives us 4 divided by 8, total possible outcome. Don't forget that the definition I gave in the last class, that probability of an event happening is number of favorable outcome divided by the total possible outcome. It's going to work in every situation that we are working with. So 4 over 8, 4 here 1, 4 in 8, 2. And that is my final answer, 2. And the last question, 2 heads, 1 tail. Just go there. How many have 2 heads, 1 tail? There are 2 heads, 1 tail here. 2 heads, 1 tail here. Here we have 1 head, 2 tails, so it's out of it. We have 2 heads, 1 tail here also. So, how many of them? 1, 2, 3. And this is going to give us 3 divided by 8. What if the question says, what's the probability of obtaining a head first? A head first. Head is first here. Head is first here. Head is first here. Head is first here. That is 4 over 8. What's the probability of obtaining a tail first? Tail is first here. Tail is first here. Tail is first here. Tail is first here. Just like that. Different questions. So this is all about event of tossing 2 coins and event of tossing 3 coins. Event of throwing a die. We all know that a die is in the form of a cube, and a cube has 6 sides to it. So by numbering the sides 1, 2, 3, 4, 5, 6, you realize that a die having 6 sides is numbered 1 to 6. So the possible outcome, the sample space of throwing a die, that is, if I throw 1 die, is either I have 1 or 2 or 3 or 4 or 5 or 6. Since 6 is the highest that we can have and 1 is the lowest. So the sample space is like this. 1, 2, 3, 4, 5, 6. Don't forget, in cases like this, we define the sample space. Like in the question of the balls in the bag, they already gave us the balls in the bag. 3 were black, 2 green, and we have 4 reds. But here, they just tell us a die was thrown. What is the probability of getting a 2? What is the probability of getting a odd number? So it is we that now have to come out and find out, okay, the first thing is to know the sample space. So the first thing to do is to get the sample space for a die. And this is 1, 2, 3, 4, 5, 6. If you have gotten the sample space, the rest is simple. What is the probability of obtaining a 2? That is, if I throw my die, what's the probability that a 2 will appear? Probability that a 2 will appear is, how many 2 do I have here? Please, it is not 2 over 6. So a 2. This one has a single entity. So how many 2's do we have here? Just only 1. So that is 1 divided by total possible outcome 6. Again, what's the probability of obtaining a odd number? So you come to the sample space. How many odd numbers do we have? Number of favorable outcome over total possible outcome. So we have 1 is a odd number, 3 is a odd number, 5 is also a odd number. So if I count 1, 2, 3, we have 3 divided by 6, the total possible outcome. So 3 divided by 6, if you reduce to the lowest term, 3L1, 3 in 6 is 2, 1 over 2. Probability of obtaining a prime number. You need to know what a prime number is. What are prime numbers? Prime numbers are numbers that are divisible only by 1 and itself. That is divisible by 1 and itself alone. 1 is not a prime number. 2 is a prime number because it is divisible by 1 and 2 itself. 3 is a prime number, it is divisible by 1 and 3 itself. What do I mean by being divisible? It divides without a remainder. So 1 in 3 is 3, 3 in 3 is also 1, so no remainder. 4 is not the prime number because 1 can divide 4, 2 can also divide 4 without remainder, 4 can also divide 4, then it's not the prime number again. 5 is a prime number because it's only divisible by 1 and 5 itself. So how many is that? 2, 3, 5. That is 1, 2, 3, and that's how I got 3 divided by 6, which is also 1 over 2. Number 4. What's the probability of obtaining a number greater than 4? Is either I obtain 5 or I obtain a 6 because those are the two numbers greater than 4. And it's easy for me to do that. And don't forget also where we were talking about the mutually exclusive events. Probability of obtaining a 5 or a 6 is going to be 1 over 6 plus 1 over 6, which eventually will give me 6, 1 plus 1, 2 divided by 6. So we need to know, just instead of doing all this, what you just have to do is count how many are greater than 4. 5 and 6 are greater than 4. So that's 2 divided by 6, the total possible outcome. So by reducing that to the lowest term, 2 here 1, 2 in 6 is 3, that's 1 over 3. Number 5, a number less than or equal to 5. So that's why I use this as x greater than 4. But here, x less than or equals to 5. So you just go there. When you see the equal to sign, it means 5 inclusive. 5 inclusive. If it is greater than or equals to 4, then it means 4 inclusive. So that would be 3 over 6 in this case, if it were x greater than or equals to 4. But in this case, it is x less than or equal to 5. That is a number less than or equal to 5. So this number is less than or equal to 5. How many is that? 1, 2, 3, 4, 5. Because it is less than or equal to 5. So 5 is also part of them. So 1, 2, 3, 4, 5. That's 5 divided by 6. So we are moving now to the event of throwing 2 dice. The last one was the event of throwing a die. And if you throw 1 die, the possible outcome or the possible sample space is 6. And don't forget, now that we have 6 possible outcomes, that will be 6 raised to power n. Sample space, since we are tossing it once, we have 6 raised to power 1, and that's 6. For this one, here we are throwing 2 dice. We are going to have s equals to 6 raised to power n, but now n equals to 2 because you are tossing it twice. The event of tossing a die twice is the same thing as tossing 2 dice once. So this will be 6 raised to power 2, that's 6 times 6, and that's 36. So if you count all the sample spaces here, I mean the outcomes here, we have 36. But that aside, how do we get the sample space? Event of throwing 2 dice, or 1 die twice. What you just have to do is draw the possible outcome for the first die, draw this possible outcome for the second die. This one vertically, this horizontally. So we now begin to see their intersection. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Just like that. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. So we go on and on. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, then 6, 5, then 6, 6. So if you count them, we have 36 of them. 6 on this side, 6, that's 36. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So if you have now gotten the sample space, the question could go in different form. Just like I said, these are just examples. It would come in any way. What is the probability of obtaining 2 odd numbers? That is, if I threw my dice twice, what's the probability that the numbers that will appear will be odd? So you just go to your sample space and find out how many are odd, and there are just 2 of them. So 1 is a odd number, 1 is also a odd number, so the 2 are odd here. 1 and 3 are odd numbers, the 3 here are odd, so this is odd. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 outcomes favoring 2 odd numbers. The first is odd, second is odd, first is odd here, second is odd. If you count that, we have 9. And that is 9 divided by 36. So 9 here 1, 9 in 36, 4. The next question, a sum greater than 10. What's the probability of obtaining a sum greater than 10? So what do we do? Just go back and start adding them together. 1 plus 1 is 2, so it's not greater than 10. 1 plus 2 is, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4, 5, 1 plus 5, 6, 1 plus 6. If you look at it that way, you realize that even up to 4 plus 5 is still 9, and we are looking for a sum greater than 10. 3 plus 6 is 9, 4 plus 6 is 10, not greater than 10, so it's still 10. If I come here, 5 plus 1 is 6, 5 plus 2 is 7, 5 plus 3 is 8, 5 plus 4 is 9, 5 plus 5 is 10. 5 plus 5 is 10. I'm trying to claim the first information. But 5 plus 6 is 11, so that is greater than 10. 6 plus 4 is 10, so it's not greater than 10. 6 plus 5 is also 11. 6 plus 6 is 12. So we have 3 of them favoring this information. A sum greater than 10. So probability of obtaining a sum greater than 10 will be how many favors that? 1, 2, 3. 3 over 36, which is the total possible outcome. So if you divide this further, 3 here 1, 3, 36, 12. That is it in a simpler form. The next question, a product less than 20. What is the probability of obtaining a product less than 20? What do we do? Product is multiplication, while sum is addition. So the product is 1 times 1, 1. So that means 1 is less than 20. 1 times 2, 2. This is also less than. 1 times everything here, they are still less than 20. So we have 6 of them there. 2 times 1, 2. 2 times 2, 4. 2 times 3, 6. 2 times 4, 8. 2 times 5, 10. 2 times 6, 12. 3 times 1, 3. This is also part of it. 3 times 6 is 18. 4 times 1 is less than 20. 4 times 2 is less than 20. 4 times 3, 4 times 4. 4 times 5 is 20. So that's not part of it. 4 times 6 is 24. It's not part of it. 5 times 1 is 5. Is less than 20. 5 times 2 is 5. Is 10. Less than 20. 5 times 3 is 15. Less than 20. But 5 times 4 is 20. 20 is not less than 20. 5 times 5 is 25. 5 times 6 is 30. This is not part of it. So we move to the last one. 6 times 1 is 6, less than 20. 6 times 2 is 12, less than 20. 6 times 3 is also what? 18, less than 20. 6 times 4 is not. So if we count that, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. That's how I got probability of a product less than 20 is 28 over 36. How many favors product less than 20? We have 28 over total possible outcome 36. Reduce that by 2. 2 divided by this is 14. 2 divided by 36 is 18. 2 divided by 14 is 7. 2 divided by 18 is 9. So the simpler form is 9. Then the next one is 2 prime numbers. So I need to clean this so that it won't confuse me. So you can use different method. You can circle one, underline the rest, and so on. But just do it in a way that will not confuse you. So I need to clean this up. Don't forget, the question could come in different ways. It could ask you a odd number first, even number next. You just count them. How many have odd number first, even number next? Like now, 1 is odd, 2 is even, 1. 1 is odd, 4 is even, 2. 1 is odd, 6 is even, 3. This is not part of it because this is not odd first. This is even first, all true. So you move to this again, and so on, depending on the question. But the last question is, what is the probability of obtaining 2 prime numbers? 2 prime numbers. Just go to the board. Don't forget, prime numbers are numbers that are divisible by 1 and itself. 1 is not a prime number, so it's not even going to work here. So 1 and others are out in the first row because 1 is not a prime number and we need 2 prime numbers. So here 2 is a prime number but 1 is not, so this one is out too. 2 is a prime number, 2 is also a prime number, so this is part of it. 2 prime numbers. 2 is a prime number, 3 is a prime number. 4 is not a prime number but 2 is a prime number, so that counters it and not 2 prime numbers. This is 2 prime numbers. This is 2 prime numbers, 2 prime numbers, 2 prime numbers, 2 prime numbers 5 and 2, 2 prime numbers 5 and 3, 2 prime numbers 5 and 5. This is out. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that is how we got here. 9 divided by 36. Simplify that to the lowest term, 1 over 4. So ultimately, what has this information do for us? How does this help us in our real life? Like I said, mathematics generally helps our logical thinking, helps us to think rightly, and even in this case of probability, don't forget earlier I said if you have one die, what you have to do is to toss it twice. Like in the Ludo game, when people play Ludo game and they have just one die, what they do is to play it twice so that they can record 2 scores. Okay, 5, 6. But if you have 2 dice, what they do is just to throw it once, and this will help them to count. They record the number on the first die and the second one, so they can start counting and moving on. So generally, probability is helping us to measure the degree of occurrence of an event. Like now, if in June rain normally falls, and last year we took records of the days that we have rain, probably we have rain 20 days out of 30. What's the probability that this June we also have rain? The tendency is that, okay, how many days did we have rain in the last one? 10 or 20 divided by 30, which is the total number of days in June. So probability that we are going to have rain today in June is going to be number of favorable outcome. How many has favored raining in June in the past, and how many days do we even have in the month? So that is 20 divided by 30. We have 20 divided by 30, and this is 2 divided by 3. So all this information helps us in weather forecasting, in predicting the future, at least to knowing what will happen, so that we can even get ready and prepare ahead. For a student who has a record of the way lecturers comes to class, he knows that he already have the records that the lecturer normally doesn't come on Wednesdays. And he slept off yesterday night, which he has an assignment from the lecturer. Well, he could be coming to school with the confidence that, okay, this lecturer does not normally come. The probability that he will come is actually very slim. So that might give him the confidence of, okay, let me just go without doing the assignment. By the time he gets to school, he can just quickly find a way. But if the lecturer would definitely come, it helps him to think ahead. I have to do this assignment because there will be a punishment for it. So probability helps us in real life in applying it to our day-to-day activities.